Good morning, everyone. My name is David Talby, and welcome to this webinar about lessons learned applying natural language processing in healthcare. If you have any questions, please put them in the questions from audience section of BrightTALK as we talk. And some questions I will just answer as we go, some questions I will answer towards the end. So let's get going. We're going to talk a little bit about really where we are and some of the changes that have happened in the NLP and text understanding work over the past really 2-3 years. And then we're going to talk about four specific lessons learned that I've learned after about almost 10 years working on different types of NLP problems, on what it takes to really get some of these algorithms and approaches from idea to production systems in healthcare setting. So NLP is one of those areas that have made amazing progress over the past few years. Part of it is just deep learning and some of the new really levels of accuracy they can achieve and haven't so far. And part of it is really just the breadth of applications in which we're able to apply it. So in 2017, the graphic that you see on the screen here began to be published by IEEE Spectrum, and they call it the AS versus doctor kind of analysis where they do, and they basically track the academic papers that compare new AIs versus kind of best of class doctor performance, and see where kind of AI is winning and when doctors are still not. And in 2017, one big kind of question that was answered around natural language processing was, okay, can you go beyond understanding kind of entities and terms and actually understand fine nuances where the doctor actually looks at you in the same room, talks to you, understands your kind of state of mind, and begins to really diagnose in a deep way. And one of the things that happened in 2017, there were 4 separate papers published that showed that computers actually do it really well, and in some ways they understand kind of really human emotional nuances better than humans do, than human doctors do. And this was very well exemplified on mental health, where computers are shown to actually do better than people in evaluating psychosis onset, in schizophrenia, early diagnosis of autism and ADHD, and suicidal behavior. And those are areas that have always been hard for humans to diagnose correctly. On one hand, so just great for the study of mental health. On the second, these are areas where, this is really not about, doing any kind of keyword matching or doing a smart linguistic algorithm. Those are areas that assume to really require understanding the emotion and the body language and the pitch of voice and the eye contact of the human in front of you. But 2017 was really a breakout year in that sense. In 2018, there was we went further because one of the big questions for AI in general and NLP specifically was, okay, I understand you can do very, very specific tasks, kind of diagnose one thing or look at one specific, for example, MRI image or CT image and answer questions, but can you kind of look at a patient as they come in and answer a broader set of questions? And there were 2 interesting papers that came in 2018 to show what's going on. Both of them were interestingly from China. One of them was an algorithm that actually passed China's medical licensing exam, which is obviously a very broad stroke at what it would take to be a doctor, many different types of cases. And also, about half of the questions in the exam were about actual patient cases. So patient goes in, presents with this, has those lab results, what should be done. And we're getting to a point where we're actually doing nicely better than kind of the average doctor that takes the exam. The other thing was a great paper around an 18-month study that involved 600,000 patients, where an AI system actually diagnosed kids as they went into the ER with their parents, which is obviously another case where kind of a very broad understanding of the patient and the parents and the situation and medicine is required. In 2019, we're continuing, and really the historical thing that's happening this year is reading comprehension and question answering, where the Stanford question answering data set, as we had SQUAD, and now we have SQUAD 2.0, and now we're starting with glue and super glue. It got to a point where for SQUAD 1 and SQUAD 2, in March, after about 8 months, we have now algorithms that actually beat humans. And this is general reading comprehension. So you get a paragraph, same as kind of SAT, reading comprehension, you get a paragraph, you get the questions about the paragraphs and need to answer it in natural language. And now we have AI that can answer this on a closed data set, on a paragraph, as well as on conversational Q&A about the paragraph, which is the COQA benchmark. So overall, as we can see, when we look at a task or we look at an area, we are now very quickly getting to a point where really within less than a year, we can build systems that either match or even exceed human performance. And the key thing is really just getting to a point where you have a specific task where you can measure accuracy and define success, and then yes, we can just go and kind of make that happen. This talk and what you're going to talk about in the next 45 minutes or so, it's about 4 lessons learned that I've learned with just kind of my limited experience in healthcare from building systems that they do exactly that in different contexts. So the first and most important thing that you need to remember if you're building a system that understands language or natural language is that all of us, we speak many more languages on a daily basis than we realize. And what I mean by that is that the way I speak to you right now is different from the way I speak to my kids, different from the way I speak to my wife, different from the way I write emails, different from the way I write texts. And I use different vocabulary, different grammar, and there's different meanings to the same words when I'm in those different contexts. Because these are really different languages that people use. These are different languages that we learned over time through jargon and social context, which means that the algorithms we use have to adapt to them as well. So let's look at a few examples. So within healthcare, so one classic thing to look at is medical records, and medical records come either digitally from an ER or in a scanned format. And when you look at a person's medical record, you want to understand symptoms, vitals, labs, the physical exams. Why did they come here today? Do they have, what are the symptoms today versus history of present illness, personal history, family history. Then, am I doing a procedure to the patient? Am I placing any orders for labs or medications? And what is kind of the plan going forward? So if you ever looked at the medical record, one interesting thing is that by average, more than half of the sentences are not valid sentences in English grammatically, okay, because there's a lot of shorthand writing that goes on. The other thing, there's a lot of kind of jargon and abbreviations that are used, which is why really, if you're trying to use any off-the-shelf NLP library or service to the medical record, usually you would see very poor results. Because really you're using an algorithm that was trained on a different language. In a completely different context, if you're trying to understand chats, so SMS, and if you look at the example here, that really is a different context and a different language. Because if you're looking at any kind of messaging system, so first of all, people do not speak in full sentences. They break sentences over different messages. They do not say who they are speaking with because it's implied by context. They speak in the first person to one another. And use emojis, which is basically its own language for expressing sentiment analysis. They use slang. They have their inside jokes and some profanity. Usually what you need is to understand several messages in context to understand really what's really happening. Okay, but obviously the words, the grammar, the style of writing used here is completely different than what was there in the in the medical record example. Another language that we sometimes use is the language used to write academic papers. And also that one is completely different from the two languages we've just seen. When you write an academic paper, first of all, usually these are professionally written and often professionally edited documents. So you have longer sentences. You generally use correct grammar. Okay, and what's important is also the structure of the paper. So the title will usually be keyword heavy, right? To say, okay, here are the main keywords and topics I'm talking about. The abstract would be usually kind of the best summarization of the paper itself, and that comes afterwards. And then kind of introduction and related work would give you background material. So really, if you want to understand what the paper is about, you don't want to read the introduction and related work. You want to understand usually sections 3, 4, and 5, where the meat of the actual advances of this paper would be. And then towards the end, you have a discussion of future work, which actually talks about work that was not yet done, and then references can be used to link to other papers that obviously are not regular text. Okay, but if you want to do things, for example, like read through PubMed and understand, okay, well, was this trial successful? What were the results? Was it double-blind? What benchmarks did they use? Also, you need to use completely different models in the previous two examples. We have quite a few examples, and this is an example of a project we've done on pathology reports. We need to extract, and this was in the oncology space, so we needed to extract information about tumors. So staging, size, laterality, body part, TNM values, histological types and grades, and so on. And you have cases where you have a scanned document, you have handwritten notes, you have tables, okay, you have kind of breakout sections within the within the text, and still you need to be able to extract the values you need. But obviously this would look completely different from just a language perspective, right? If only because the handwritten notes have to be kind of linked to the sentence they come from to understand the context. And while we're in healthcare, obviously there are other formats that we need to parse. So in this slide you have two others. You have emails and you have fire messages. And really what's important to know is that here you can see an example on the screen of the kind of text that you actually get, okay, which obviously is structured, at least semi-structured. And obviously you need special parsers to just be able to read the message, understand what's in it, until you get to the point where you actually have free text in the email or say in the note section of a file message, where really you deploy a kind of more classic NLP algorithms. Okay, but in general, here's what happens. I'm yet to see a project in healthcare, or say even outside healthcare, where you can take pre-trained NLP models or algorithms and just apply them as they are. Usually the first thing you need to do if you're starting a language understanding project is really understand what language you're processing. Okay, and it comes down to vocabulary, to grammar, to context, to meaning, and be able to just train your algorithms to that. And here on the slide you see some examples of kind of the specific algorithms or specific types of models that you need to train. And really what happens is that basically for each of the examples we've just seen, you will need to train even kind of what's considered very basic NLP algorithms like spell checker, part of speech tagger, definitely things like name entity recognition, sentiment, or negation detection. Otherwise, you're going to see very poor results in terms of accuracy in practice. Okay, so that's the first thing you need to pay attention to. So the next thing that you need to realize, and this kind of just follows naturally from the fact that your project will probably use its own language in order for the documents you're analyzing, is the fact that you will need to train your own models. And the reason you need to train your own models is because if you try to use any off-the-shelf models, and usually these are the first questions which I usually get, why can I just use this specific library or open source code or cloud service? And the answer is really simple. Don't believe me, try it for yourself. And as you see, the accuracy number will just not be there. It will not even be reasonably there where you need them to get a successful project going. Do not believe me, please. Let's be data-driven. What you should do is look at the documents you have, look at the use case you have, and actually try it. Here are the links, and after this talk, I'll be able to share a link to the presentation as well, so you'll have the hyperlinks. If you don't, you can just Google those examples. Those are kind of some of the main open source and libraries and cloud providers in the NLP space. And all of them, except for Amazon, publish a nice demo UI where you can just paste your own sentence or paragraph and see how the algorithm performs. So you should do this because it will take you exactly 2 minutes to use this demo UI and see what results you would get. And really, in most cases, what you would see, that those pre-trained algorithms and libraries or cloud services will just not give you results that are useful, especially in a healthcare setting. Here's one example that we worked on a couple of years ago, and this looks at emergency room triage notes. So if you look, for example, at the first example, state started last night, upper ABD, took Alka-Seltzer, approximately 0,500, no relief, nausea, no vomiting. So this is kind of the classic abbreviated shorthand style of notes that people write when when their patients are in the ER. What's interesting here is that if you look at all of these examples, none of them none of them include the word patient, none of them includes the word pain, because it's obvious by context. None of them are valid English sentences. They use different types of abbreviations, so approximately 0,500 probably means around 5 in the morning and not 500 milligrams. You have other kind of symbols here, like 10/10 usually means level of pain. And there's a mix here between kind of what happened to the patient, when did it start, kind of where does it hurt, how much does it hurt, what are the other symptoms, and did you already take some medication at home so that we don't overdose you. On this specific example, and this is true as of December 2018, so last December, of the 6 engines that you saw in the previous slide, 2 of them were able to recognize the Tylenol was a product. And that was it. That was all they can do on those 3 specific examples. So if you're really trying to understand, okay, what happened to this patient, why are they here, where does it help, what do I need to do, obviously, this is not going to help you in the least bit. Another thing to consider is even if you have a healthcare NLP model, what happens in healthcare, especially this happens in general, but especially if you're dealing with language, that models do not generalize well. And this is not an issue with the algorithm. This happens because, in general, in healthcare, people practice medicine differently from hospital to hospital and provider to provider. Okay, and people write things differently. Okay, so if you are, if you're looking, for example, at oncology department hospital A and oncology department hospital B that's across the street, most likely they have different patients, they use different clinical guidelines, they specialize in different things, they order different tests, and they also write, they use different templates, and they train the doctors to write different things in their notes. As a result, even if you have a model that's 99% accurate on hospital A, you may see it 20 or 30% accurate on hospital B. And what's unique in healthcare is really how dramatic those gaps can be, and how hard it is to really generalize models. So here's an example of a project we did a few years ago on clinical coding. So this tried to do automated ICD-10 coding, and basically on the easiest use case, which is outpatient radiology. Okay, so this is you go and you do an X-ray or CT scan, and the first goal in this specific diagram is really just to extract what the procedure was. So this CT scan of the chest, with or without contrast, and so on, and map the correct CPT codes. And we worked here with the with the radiology shop that did basically outsource coding for 24 clients. So it's the same set of people doing this work for 24 of their providers, their clients. And here's you see in the graph one typical example where we trained the model for client A, so one team of radiologists, and we had the model was around 90% accurate and almost 90% in terms of recall. So around just over 90% precision, just under 90% recall. And using that example, and this was typical on another one of their clients, this kind of pre-trained model on another client got us around 50% precision and 10% recall. And just to understand how bad it is, 50% precision means that the algorithm is wrong half the time. 10% recall means that in 9 out of 10 cases, the algorithm just doesn't return an answer at all. It just doesn't know. Okay, so basically you're moving from from a model that gives you an answer 9 out of 10 times and is correct 9 out of 10 times to a model that gives you an answer 1 out of 10 times, and when it does, it's wrong half the time. So it's essentially useless from a practical perspective. And these are kind of the dramatic gaps you'll see. So really, oftentimes in healthcare, the problem is not how do you build one model and have everyone use it, but instead, how do you make it really easy to localize and tune a model for a new hospital or new customer or new pair, so that really you can get those good accuracy results and scale it for a large number of customers. So you will need to train your own models on your own data, ideally data that's localized to the specific kind of customer implementation you're doing right now. And you definitely, as we talked about, assume that a model that someone built and has done amazingly well in a paper or in implementation elsewhere will work for a new data set. So how do you know how you're doing? So let's say you have a new data set or you have a new customer from an existing model. The first thing you need to do is just annotate and label data. Okay, and to do that, you need to pair your NLP or in general your data scientist with a clinician. So with a domain expert that understands the specific language that that you need to understand. Okay, so if you're doing clinical coding, you want to have a clinical coder who understands radiology. If you're doing fraud, you want someone who has been doing fraud for a decade or two. If you're doing oncology, you want an oncologist, and if you're doing pathology, you want a pathologist. One of the mistakes people sometimes make is that there are some cases where they assume that this is going to be easy, and therefore they do not need specialists. Okay, and here's one example. In this example, we're trying to we're just trying to rate a restaurant review. So this is an actual review of a Mexican restaurant from Yelp. And let's say that our algorithm needs to predict whether this is going to be 1, 2, 3, or 4, or 5 stars. The issue here is not that this requires 8 years of medical training to answer. The issue is different. The issue is that different labelers or basically different humans will give you different results. So some people will look at this and come and say, oh, this is 4 stars. Some people will say this is 3 stars. Some people will say this is 5 stars. Here's the problem. If the rate of agreement between you labelers, you judges, is let's say is 80%, this means that 80% is the upper limit on accuracy that you can theoretically get on this problem. Any model that you have that is more than 80% accurate is by definition overfitting to noise, right? Because really, if you ask your team the same question again and again, you're not going to get more than 80% agreement. Okay, that means that your problem here is not around the model. The problem is how do you actually increase agreement, which requires people who are domain experts. In this example, you need people who really understand the domain of what does it mean to take restaurant reviews and map them to a specific star rating. And you need to make sure that your team really understands the nuances, every nuance of what do we really consider the difference between say 4 and 5 star review. Okay, so this happens outside healthcare, definitely within healthcare. If you have a team of say oncologists, You need people to agree on the edge cases of what does it mean to be in a specific stage, right, of cancer, or have specific TNM values. So the next question that always gets asked is, okay, I get it that I need to labeling, but how much do I need? And the answer, of course, it depends. It depends basically on the complexity of what you're trying to do. So for example, if you're trying to do automated clinical coding, outpatient radiology usually means that you're selecting one of usually less than 100 different procedure codes. Okay, so if there is a CT machine in the room, it's only going to be one of the CT procedures that are going to be applied. On the other hand, if you are looking at kind of general medicine, pediatric medicine, internal medicine, basically more things tend to happen within those specialties, right? There's just more variety. Because there's more variety, you're going to need more, more labels to do this. In general, today we transfer the, with the advancing transfer learning, usually need to do really well with even just having, several thousand labeled examples. So this is kind of the rule of thumb of what you should aim for. So at least have several thousand examples that you actually labeled. The two most important things to consider is what's here on the slide. Make sure you get representative data. Okay, so make sure that you have enough men, enough women, enough kids, enough adults, enough different stages of the disease, right? So for example, if you're looking at diabetic, make sure that you have people, with the history of blood pressure, no blood pressure, type 1 and type 2 diabetes, different genders, ideally different, ethnicities, different previous conditions. Okay, so that really your data represents the real world. That's one thing. And the second thing, as we already talked about, is make sure that the labels are consistent. Okay, make sure that you should really worry about the agreement between different judges and different labelers in your team, because that's an upper limit on the accuracy that you can expect to achieve. Okay, so you know that you need to kind of train your own models. You need to start by annotating data. Let's assume that you have the data, it's labeled, and now the question is, okay, let's talk about the actual libraries and actual algorithms, or kind of what do I need to do now to actually go and build NLP models? The good news is that basically, and this is the third thing I want to talk about, is that basically transfer learning has gotten basically good enough in healthcare that in general small data works really well. There are quite a few cases where even just having a few hundred labeled examples can give a very good result in terms of accuracy if you use the right transfer learning techniques. And this is great. First of all, because annotation, as we said, requires domain experts. So it's fairly costly and time-consuming to do. The other thing we have in healthcare is the compliance issues, right? So in general, in healthcare, your customers, or if you're doing research projects, basically the people who own the data, would not allow you in general to take the data out. It would not allow you to mesh the data with other patient data from other information, right? Because they either don't want or they're just legally not allowed to share it. Okay, but the good news is that you may not need them to share it. Right, so you can go into a new hospital, and in terms of instead of telling them, oh, give me your last 5 years of data, and I'm going to, share it with all the data I got from other hospitals and be this huge big model, you can tell them, look, I don't want any of your data. I'm going to install the software inside your environment. We're going to label, say, a couple of thousands of cases. I'm going to tune models to those 2,000 cases and give you the results you want. That's it. And that's really the recommended way of working. Makes compliance much easier. So in terms of how you'd actually train the models, so my team has been working on the Spark NLP library. We've been working it for well into the third year of working on it. And when we started, the goal was to really to build an open source library for state-of-the-art NLP. Because two things happened in the NLP world in the past 4 or 5 years. One of them is deep learning, as a result of which many of the existing open source library way behind in terms of accuracy in what you were actually able to achieve in practice. The second thing that happened was because of Apache Spark and some of the work that was done both on single machines and on cluster, basically we saw that we could achieve 1 to 2 orders of magnitude of speed up, even before you start putting GPUs in, and of course another couple of orders of magnitude after you put GPUs in. And having that level of speed that makes a huge difference in terms of how fast you can experiment and optimize your models. So Spark NLP earlier this year in February 19, O'Reilly did a survey and found out that it's basically, it's the most widely used NLP library in the enterprise. It has Python, Java, and Scala APIs, and you know, at least the core library is completely open source and used fairly heavily by a growing community. One of the things that you do care about is accuracy, right? You can say, okay, look, I understand that I need to train custom models and build my pipelines and such, but where are the algorithms? How can I actually achieve top accuracy once I do it? And Spark NLP, one of the things we aim for is really having state-of-the-art results. And state-of-the-art means that basically what you want to do is you want to read the latest academic papers, see the best performance approaches on kind of public academically accepted benchmarks, and that's what you try to reproduce and productize and make widely available. So for example, name entity recognition. So for example, looking at the free text medical record and extracting the symptoms, procedures, labs, adverse events, medications. The goal is really, the goal is obviously to be as accurate as possible. And right now we are, we are that position for the open source field, right? And what it takes is obviously, first of all, it's about which algorithms and which papers we implement, right? And right now, kind of the reference implementation is bidirectional LSTM for tokens, CNN for characters, CRF, and the use of embedding. We have built embeddings kind of implemented within the algorithms. We use kind of custom layers within TensorFlow. We're able to make this scale and trainable within GPUs, and we regularly retrain some of the models that are used for transfer learning. Okay, so we've done lots of work in that space. So accuracy-wise, this is one kind of open source way, completely free, that enables you kind of to get the core algorithms that you want to then train your models on. The other thing you would care about is speed and scalability, and also there are links here to public benchmarks that were published online. So one was kind of a 15-page thing that was published on O'Reilly Radar. There were a couple of other blog posts and articles that measure both speed on a single machine and then scalability on a cluster to show what this library can do. And this is obviously something you care about because if you're training your own models, you need to train multiple times, look at different data sets, do hyperparameter optimization. So making sure that you can experiment quickly is of course critical in any data science case. So there's a set of papers and reasonably new papers that the library implements, and right now we're working on things like ExcelNet and ERNIE and kind of the latest and greatest innovation in the NLP space. So that's definitely something you want to have with you, right? So there's, okay, I want the best and brightest kind of deep learning, deep embedding, and related algorithms implemented from a software perspective. I need it to be trainable, okay, because now I'm going to bring my own problem, my own documents, my own label data. And then the question, and then really what you want is you want to make sure that you have, your library can give you pre-trained pipelines so that things are easily trainable. Okay, so here's an example, and this is what often happens in real projects, about what you can reuse and take from kind of the open source community or existing algorithms or papers or products versus what you need to do yourself. So first on the left, here's what you will need to do yourself. So you will need to train custom models for each use case, okay, as we discussed. You may want to change the NLP pipelines because sometimes you may need OCR, sometimes you don't. Sometimes you may need speech to text, sometimes you don't. Sometimes there are going to be specific entities that you care about. Okay, so sometimes you care about medications, sometimes you care about tumor data, sometimes you care about modifiers for specific clinical codes. So what you want a library where that is trainable. Okay, and ideally that library should have two important features. First, you want to be able to run it on premise on your own data, so that you don't have to share it or send it anywhere. That from a privacy and compliance perspective, would make your life much easier. The second thing you want to do is usually, even if you have access to full patient data, you want to de-identify it before you train models. Because even if you're not legally required to de-identify, if you train on unidentified data, you have the risk of the machine learning models learning based on identified information. For example, one thing that algorithms tend to learn from is doctor names, okay, because doctors specialize. So if you are, for example, in oncology, and you have a doctor where all they do is they do, they remove neck tumors for patients who are at, stage 2 or 3 in terms of where they are in their cancer, then your algorithm will learn that if the doctor's name is mentioned, that the patient probably has stage 2 or 3, for certain types of neck cancer, which is technically correct, but obviously generalizes horribly. So those are the kind of things you want to make sure you remove from your data set before you train. Now, the things you can reuse are basically, here on the right are two things. First of all, you want to make sure that the actual neural networks, the algorithms, the more basic NLP algorithms, right, like medical part of speech, medical OCR, medical spell check are already there for you. Okay, so you would want, whichever library of service you use, you want to make sure that the algorithms are implemented, the algorithms are state-of-the-art, that there are some fairly fresh pre-trained models that it comes with. And that's what you use as the basis for your own trainable pipeline. The second thing you want is data. Okay, so you want someone to give you kind of current and pre-trained model, medical terminologies, and deep embeddings that are healthcare specific. Okay, and and that's basically your recipe. So you combine the reusable parts here, which you can get. Sometimes you can get free. Sometimes you can do it via service or license, with a usually customizable NLP pipeline, and label data for your own specific problem so that you train your own custom models. Here's one example, and this is a case study that was published at the Strata Data Conference in March this year with Roche, one of the teams at the pharma company Roche, around automatically extracting oncology information from pathology reports. In this example, actually Spark NLP was used to extract actually about 65 specific fields, and this is kind of specific tumor information that was interesting. So the project was first we had to kind of have the clinicians agree on the clinical guidelines and terms, annotate a set of documents, and then train the algorithms that are now able to automatically extract. It's fairly good accuracy, which obviously depends on the specific field, those values, those structural values from reports. What you want to do is, for the algorithm, is first of all identify the terms, extract those specific terms, for example, the margins of a tumor, TNM values, pH levels, other test results. And the second thing that's very important is to normalize. So if it's a lab result, you just want to normalize it to specific unit. If it's a symptom, diagnosis, or a procedure, usually what you want to do is normalize it to a code set. Okay, which is commonly things like SNOMED, RX norm, LOINC, or ICD, at least in the US. And this takes care of things like synonyms, writing this, basically using different words to say the same things, spelling mistakes, right, and sometimes different kind of different versions of the terminology or ontology that you use. So that instead of relying on, for example, removal of lesion of colon as a string of text, so that whenever someone writes it slightly differently, you have two different features, which would make your feature space much shallower. What you don't use is a specific code, right? So ideally the specific ICD or SNOMED code that applies to it, and then you rely on your NLP library an algorithm to make sure that all of the different variants or spelling mistakes of, say, a procedure are mapped to the same code, and then you have kind of much stronger features in terms of the codes to train on in the next steps, right? So, for example, assuming you actually use this to, to predict patient progression, predict patient risk, recommend a clinical guideline, look for anomalies, and so on. Usually, at that point, you'll want to use mapped entities into standard code sets. Okay, so the fourth thing I want to talk about is what you do with the data you've extracted. So far, okay, let's say that we are able to read, say, clinical trial data for inclusion-exclusion criteria, or we can read radiology reports, we can read CCD data, certain kind of file messages. But let's say there's a set of unstructured documents. You understand the problem you're working, you understand the document, you've annotated them, you've trained fantastic state-of-the-art models, and you're able to extract data. Okay, so you're able to understand what is happening to the patient, what are the symptoms, diagnoses, labs, what stage they are in, what risk they are in. Now, usually, almost always, that's not the end of what you're trying to do, right? So nobody just wants to extract entities. Usually, this is just one part of the real problem you want to solve. Okay, so for example, my problem is that I want to understand patients at risk. Okay, I want to understand, what's the prognosis for this patient, right? So how long before they get better, right, or get worse, right, depending on kind of what the condition is. Yeah, so usually what you do is you use the features that you get from NLP or the answers or the insights you got from the text, usually as features or the stepping stone to kind of the real predictive problem or recommendation problem that you want to solve. And in this case, one of the things that you need to realize is what this slide says, is that, in that sense, there is no such thing as an NLP problem, right? Because first of all, usually, and the NLP aspect of the problem will just be part of what your application is really trying to achieve. Okay. The other thing, you usually do have some structured data available, right? So if I'm looking, for example, for patients in the emergency room, I have, unstructured data, right? So if there's triage notes and kind of, what they talked about and what the doctors and the nurses wrote about. But I also have structured data, right? I have some, I have their age, the gender, the code that was assigned to them, the insurance plan, and really, and ideally, you would want to use that data as well. So really, the way to look at the actual problem you're trying to solve, beyond the NLP piece, is always about how do I combine the structured and unstructured data correctly and effectively, right, to solve the problem that I have. Let's look at a couple of examples of how that happens. So this would go back to the ER example we spoke about earlier. So in this example, in this project, what we had to do was do hospital demand forecasting. So the question is, okay, within my hospital, how many open beds do I expect to have in, say, in the next shift, so in the next 12 hours or the next 24 hours, and how many nurses of each type do I need? Okay, and to do that, one of the big open questions is what's happening with the people in the emergency room. Okay, because some of the people in the emergency room, let's say they have a broken hand, so just going to get a cast and go home. Some of them are developing a heart attack and are going to stay at the hospital for 3-4 days. So I need to tell between them. Okay, and to do that, the first thing you can do is only look at structured data. So when someone is in the ER, you have age, you have gender, you have vital signs, you have how long they've been waiting, and you can see if they have previous things like previous visits to the ER in the past 30 days, 60 days. And that will give you a baseline. Okay, so people who are older, people who come here often anyway, and people who who already have kind of abnormal vital signs are more likely to stay. Okay, and those are good hints. And that will give you a baseline. The baseline is not going to be very good because those features or those data points do not actually tell you what that patient is here today. Okay, kind of, is it related to what they had last time, or is it something completely new and more serious? The only place that actually has the data is the unstructured notes that the doctors and the nurses write. So you wouldn't want to be able to use NLP to basically read and understand those notes. But then once you do it and you have those extra features you extracted, what you want to do is combine them with the baseline model you built in the previous stage and basically see better accuracy. Right, so that's what we've done here. And in this example, we're not able to publish kind of exact numbers, but we have seen that basically adding the NLP features to the baseline model improved the F score by about 12 points, so about 12%, which, if you're familiar with this space, is huge. Which clinically makes sense, because most of the clinical information is within the free text. Okay, but the important point is that you combine your NLP pipeline and then your machine learning pipeline. Right, so from NLP you extract the clinically interesting features, but then you add the structured data, and now you have structured data from elsewhere, say vital signs. You have structured data that are the result of your NLP pipeline, and then you feed those into your, in this case, time series forecasting problem to see how many patients and how many beds do you expect to need within 12 hours or 24 hours. Okay, and that's kind of that's the standard mechanism of how that gets done. Here's another example. This is an academic paper that actually was able to publish kind of specific accuracy numbers. And this is the very popular problem of detecting sepsis. So this is a very common kind of predictive analytics problem that is actually deployed in quite a few hospitals because sepsis is kind of a state of severe infection that does kill people at hospitals. And early detection of sepsis is key, so that we can give antibiotics or otherwise help patients kind of prevent going into sepsis in the first place. And what was done here is the authors of this paper basically took a baseline model that looks demographic, look at vital signs, look at medications, look at all the structured data they have available from the EHR, and add the structured data, add unstructured data, and they saw accuracy jump from 0.67 to 86, which basically means, look, this goes from usually anything below 0.70 you just do not use, it's not good enough. 86 is basically state of the art. Anything over 0.9 is kind of suspect overfitting, and this was another kind of great example of showing how you can use natural language processing to basically improve baseline algorithms. In this case, in the area of patient risk prediction. Okay, so this is in general what you'd want to do. So one really serious best practice is to make sure you can actually unify your NLP and machine learning pipeline, and really make sure it's the same pipeline. Spark NLP is one library that actually enables you to code this as one library. Is one pipeline that is realizable, distributed, reproducible, and that's one of the things that you want to make sure happen. So we are at time, and we are even running behind a bit. So this presentation will close in a few seconds. There are a few kind of specific questions here. If you have additional questions, please post them after this kind of session ends, and I'll be able to. I'll do my best to reply to them either here, kind of within the text, or over email if necessary afterwards. I do wish you the best of luck with your own project. So do try to pick a project that enables you kind of to start with structured data, extend with your own custom trained NLP libraries, NLP models,